All right. Hello and welcome, folks. Again, we are using today's lab time to go over lecture content, meaning we have to talk about thermochemistry. I made this decision this morning. I'm sorry I didn't get it out to you sooner. I was thinking about our general timeline and what I want us to prioritize and focus on. We have a lab that we just completed that relates to thermodynamics, and we haven't talked about thermodynamics yet. And I don't think it's worthwhile to do two kinetics labs when we could use this time today to talk about thermodynamics and then use this lecture content to go back and look at our thermodynamics data for the borax lab. So that's what I'm envisioning for today. I am recording this, like I'm doing a screen recording right now. I feel bad for you guys that might watch this later because I'm like shouting at the classroom and then also into the microphone on my iPad, so keep that in mind. But yeah, so this is going to be lecture. Are we ready to take lecture style notes?
Well, let's just do it.
Okay. So we are talking about thermodynamics. Does anyone have a sense of what thermodynamics is? Rami? Okay, so Rami's saying thermo. This looks like heat, temperature. Yes. Gabrielle?
From what I can see, it has to do with temperature and other sorts of stuff, but I think it has to do with basically the general workings of energy when it works on other, like on reactants or products, basically stuff like that.
Yeah, so Gab said, why just heat and temperature? Why not just generally energy? And I would agree with that because in Gen Chem 1 and Chem 210, we did a lot of calorimetry. We talked about heat exchange, but we didn't talk a lot about like energy in general as a big concept. So that's the purpose of this topic in Chem 220, is to revisit our understanding of energy and to expand it so that we can explain some of the more like interesting parts about how energies evolve during some kind of chemical process. So before we even get into like any new content, I want to introduce some thermodynamic assumptions that we make in chemistry, meaning like these are some things that I want to make a statement about and then not bring up again until we deviate from them. So the first thing that we assume is we are going to assume that unless stated otherwise, the materials, our reactants, products, etc., exist, capital backwards E, in their standard state conditions. This was indicated in Gen Chem 1 with like a little knot, right? So you might remember like the standard heat of reaction, standard heat of formation, standard heat of neutralization. But let's identify what these conditions are, because they're not the same as like the standard conditions under which we talk about an ideal gas. So first and foremost, if we are talking about standard state conditions, then we presume that the temperature at which some process occurs is room temp, 25 Celsius or 298.15 Kelvin. Okay, if we're talking about a gaseous substance, we assume a standard state pressure for this gas. Anyone have a guess or a thought as to what we might assume? 1 atmosphere, very, very close. It was changed in, I think, 2022 to 1 bar, which is very similar to an atmosphere. I I believe that's 1.0135 because it relates to the Pascal. Okay, if we're talking about a solid or a liquid substance, what do you think we're going to assume about them? Rami?
Like what's their state?
Yeah, so for solid or liquid, what can we say about that state? Are we a mixture? It's going to be a what? An element. Yeah, we have solid elements, right? So when we're talking about liquids and solids in thermodynamics, we are assuming that they are pure solids and liquids, right? We're talking about elemental substances or pure molecular substances. However, if you've been alive for the past, 2 months, we've rarely even talked about these condensed phases, right? Yes, Tara, question.
So if it's not like just pure elements,
No, we could talk about like pure sodium bicarbonate, right? But we have to assume it is in fact pure sodium bicarbonate, right? It can't be a mixture of two different solids. So for the past 2 months, have we cared about condensed phases like solid or liquid? All right, let me rephrase that. If we had to find a theme for what we've been talking about in Chem 220, what would you call it? Equilibrium. Thank you, Miku. And if we're talking about things that are in a state of equilibrium, have we been talking about any reactants or products that are solid or liquid? We have? I mean, yeah, they're in the reaction, but are they in the equilibrium constant? No, right? So most of what we've done has been thinking about aqueous, something in solution. So if we are aqueous, what do you think our standard state is going to be assumed to be? How do you describe a solution? Liters are involved. Yes, thank you, Rami. Brianna, what else?
Volume.
That is what liters are. They're a volume unit. But Brianna?
it's mixed.
Between solute and solvent, and how do I describe a mixture of solute and solvent to you? If I were to hand you a sodium chloride solution, what information would you want to know about it? Concentration, which is not just liters, but moles per liter, right? So we are going to assume that if we are an aqueous phase substance, that our concentration is exactly 1.00 moles per liter. So again, this is what we're going to assume unless we're told we're at non-standard conditions. Okay, the next assumption. Is that chemical reactions are chemically reversible, but not perfectly thermodynamically reversible. So what does it mean to be chemically reversible? Iyad?
Like
like that one thing we did where we mixed the acid and the base, and then we or it was something like it was like
Okay, yes, so we're looking at a mixture or a reaction of things, yes? And again, what's the theme of Chem 220? Equilibrium. So when we're talking about a chemical reaction at a state of equilibrium, then we're talking about a chemically reversible process. I can have reactants going to products, and then also products reforming back into reactants, right? I've got my starting material, my ending material, and then that constantly shifts back and forth at equivalent rates. That's what it means to be at equilibrium. So you could think about this as like a material reversibility. I can always reform, let's say, a solid, if we're talking about KSP, from the ions in solution. So we looked at silver acetate in our KSP lab. I can always reform solid silver acetate in a saturated solution of silver acetate from the ions of silver and acetate that respectively existed in solution. Same for the forward reaction. I can always take a crystal of silver acetate and dissociate it to form silver ion and acetate ion in solution. It's a material-based reversibility, aka matter. Oh my God, there we go. So then what's the difference? Like, why am I making this distinction between something that's materially reversible, aka a reaction that could exist in equilibrium, versus this idea of being thermodynamically reversible? Do we have any thoughts? What did our initial impressions say about what thermodynamics involved? Heat, and also, generally, Ivy, thermodynamics involves the study of?
Phases?
Yes, and how changing phases requires or releases some amount of energy, right? So not just limiting ourselves to thermal energy, Iad, we're now extrapolating that to this idea of like energy in total. So if thermodynamics is the study of energy, energy exchange, energy consumption, then what does it mean to be thermodynamically reversible? Yeah, Iad. Yeah, meaning like if I were to think about a chemical reaction proceeding in the forward direction, the amount of energy that's changed, used, consumed, etc. in the forward is probably not, like, realistically completely recoverable in the reverse reaction. Like, yes, we can make conditions so that we do have equilibrium conditions where we have thermodynamic reversibility, but the reality is that's not how efficiency works, right? So the reality is that energy isn't perfectly conserved during a reaction. And this is kind of like a statement about overall, I could look at some tiny amount of energetic exchange happening in the forward reaction and then immediately reverse that step. And then like that little micro change, I could probably say is thermodynamically reversible. But on the whole, overall, thinking about how a system at equilibrium exists, like in the beaker at your lab bench, and all the energy involved in being at equilibrium, it's going to be inevitable that not all of our energy is going to be conserved within that chemical reaction. questions so far? Yes, Tara.
That also has to do with equilibrium, right?
Right, that's the idea, is I can have this material equilibrium that is a reversible process. That's what it means to be at equilibrium. And yes, if I look at like little tiny changes in energy in the forward, I should be able to reverse that little tiny change backward and get my energy like forward and reverse to be equal but opposite signs. But the reality of how energy works is like on the net scale, like the big picture in my solution, is even though I might be at chemical equilibrium, I might not be able to completely recover my initial energetic state. Jose.
So like you can't conserve all the energy, like what happens to it? 'Cause like I thought that like it has to be conserved. You can't just like
Fantastic question. So Jose asked, like, if the energy isn't like perfectly conserved, then how does that even work? I thought energy was conserved. We're going to talk about it. So let's talk about our third assumption, which is that our system is going to be some kind of chemical reaction, which means that the surroundings is everything that is not the chemical reaction. So if I'm considering, for example, like an aqueous reaction, so something that happens in solution, I only care about the reactant and product particles themselves. That's what my chemical system is. The surrounding water, the surrounding atmosphere, you, me, the experimenters, the temperature probe, none of that is what we're going to call our thermodynamic system, because that's not what is chemically interesting to us. We are just the surroundings. There's another piece to this that might add like a little bit of detail when we start talking about chemical reactions in like kind of a, I don't know, more like change of state type way later. And that's that the system in a chemical reaction is what we call the reactants, which means the surrounding is the resulting products and everything else. So if you remember from calorimetry, how many of us did styrofoam coffee cups and thermometer stuff in Gen Chem 1? Okay, yeah, that was calorimetry, right? Heat measuring. And when we talked about like the heat of dissolution, so I'm sure you guys probably dissolved some sodium hydroxide in water and looked at how the temperature changed when you did that. I know my class did. We thought about the thermodynamic system as being the solid sodium hydroxide to dissolve, and the surroundings then the resulting sodium hydroxide solution made from that initial system, because it was the sodium hydroxide solid itself that had to evolve, exchange, absorb some type of energy in order to become dissolved in the first place. Okay, and then lastly, not in sequence, sorry about that, but this is a big one because it makes our life easy. Anytime we're talking about a chemical system, and thus like the thermodynamics or energetics of that system, we are going to assume that that system exists at a constant pressure. So let's think back to all the times we've done an experiment in this class. Have I ever made you create like a hyperbaric chamber, aka a room where the pressure is really, really, really high compared to normal atmospheric pressure? No. Have you like made a vacuum in which a reaction occurs? Like, yes, we've used vacuum suction, but did I make you do a reaction under vacuum conditions? No. Anytime we've done a reaction, it's been like exposed to the lab air, meaning we've been exposed to atmospheric pressure. So this assumption is more for like sake of ease and also kind of practical reality. So the conditions of a thermodynamic system exist at some constant pressure. Ideally, exactly atmospheric pressure. But whatever that is from a given day to day can vary just a little bit. How are we doing with these assumptions? Amazing. Okay, Rami's doing amazing. All right, let me see if it's a 5. 5 is like, I get it. I get where we're coming from with these assumptions. 4 is like, I guess I understand them. I just don't know why I care. 3 is, why are you talking about this? I don't even know what a standard state is. You get the rest. So let me see. Fist of 5. How are we doing?
Sort of in the middle-ish.
Okay. Seems like we're all right accepting these assumptions at face value, but we don't know why they're useful. How about I show you? Yes, Tara, question. These are assumptions that we are going to make in Chem 220. Unless you want to derive the full body of thermodynamics like we're in physics, is what I thought, right? Chemists are cheap and lazy. Let's make the conditions set so that we are thinking about systems like a chemist. So with that, let's remind ourselves about what thermochemistry is. How is thermochemistry different from thermodynamics? Yeah, matter matters, but anytime I'm talking about energy exchange in general, it's typically between, like, stuff. Yeah? So again, what is it that we were measuring when we were talking about energy in Gen Chem 1? Okay. When we talked about thermochemistry, this was a study of how heat and just heat or thermal energy is consumed, transferred, required, whatever, during a chemical reaction. So if we had something like over here on our right, our little chemical system that then went to everything that was not those reactants, which is the product and everything else. Putting those together would give us everything in the universe. Reactant molecules plus everything that's not the reactant molecules is everything. And we often looked at the exchange of heat or differences in temperature. However, temperature changes were not like the only thing talked about. It was what we mainly focused on because it's what we could measure directly, but where did we get this from? So let's talk about these variables up here, U, Q, and W. So let's define the total internal energy U of a chemical system. Let's break that down. What does total mean? Yeah, Evan, you went like this with your arms. Okay. What do you mean? Like all of it. Internal. What, Nico? Inside. So all the things inside. Specifically, what things are we talking about here? Not just heat, but total internal energy. Make it less specific. Energy. So the total internal energy of a system is the total amount of energy content in that system. So what kinds of energy can we find in a chemical system? So like let's say we've got a bunch of ions in solution. What types of energy could we find those ions possessing? Kinetic energy. Who said that? Iad. So what does that mean, kinetic energy? Yeah, the energy associated with motion. We have to remember that when we're talking about especially our liquid, aqueous, and gaseous phases, all of our molecules and or particles are in a constant state of random motion. So there's definitely kinetic energy. Okay, we have potential energy. So Miku, what is potential energy? Yeah, or like the energy that you have stored. So we can think about potential energy in like a physics sense as being the energy based on your arrangement. So for example, if I were to take this stapler and put it on the floor, you'd be like, wow, amazing, stapler on the floor, no big deal. But then if I were to get up and put this stapler on like Iad's head, here, what do we notice about this? It could fall. We understand innately that the stapler now has a different potential to do something compared to if it was on the floor. That's what we call potential energy. Thank you, Iad, for humoring me. What else?
Thermal energy.
Thermal energy, right? If it exists at a temperature, there's got to be some innate thermal energy. If we were to zoom in on those molecules, we would see that those molecules are not just like moving around translationally, meaning going from point A to point B in the beaker, but they're also constantly freely rotating. So we have rotational energy. And if we're looking at atoms that are connected to one another via a chemical bond, that bond is not like a fixed, rigid thing. It's not like my eye pencil here, Apple Pencil, that is just constantly a straight line that connects my two atoms, my fists. What we see in real life is like spring or harmonic motion that exists across this bond. It's constantly wiggling. So we call that vibrational energy. And depending on the system, we could go on, right? Depending on the material, we could keep listing the types of energy we could find. So if we were thinking about like a solid crystal, we could talk about the lattice energy. If we were talking about a system that was fluorescing, we could talk about light energy. But the idea is that total internal energy is the total amount of energy that is possessed within your system. Now, this is general college chemistry. This is an upper division physical chemistry. So we are not going to think about things like rho vibrational energy. Rather, we're going to focus on things like kinetic energy, thermal energy, potential energy, with the understanding that like the amount of kinetic energy is directly proportional to the thermal energy. Things move fast, system must be hot. So from Gen Chem 1, we can say that the total internal energy of the system could be expressed as what? What two energy terms do we use to describe a chemical system? Robin? I didn't hear you. What? Q plus W. Okay, so total internal energy is equal to Q plus W. What does Q stand for? Heat. I promise you the heat equation is going to show up on the MCAT one day. So Q equals MC delta T. Yeah, MCAT equation on the MCAT, exactly. Okay, what's W? Work. Now in physics, work is generalized as like the ability to do like or exchange energy, meaning like the ability to maybe apply a force over some distance. In chem, we don't care about like an old lady pushing her shopping cart through Safeway, right? That's not what chemists think about. We think about molecules. So typically when we're talking about work in chemistry, we're talking about pressure volume work. Which is something that involves the expansion and compression of a gaseous system or even a fluid system. And this is equal to the negative external pressure, aka room pressure, times the change in your gaseous system volume. There we go. So this should be a bit of review. Are there any new terms to anybody here up on the board? No questions? This is all old news.
What was the last thing you wrote?
This?
Yes.
So Anthony's asking what negative P external delta V is. This is pressure volume work. So in chemistry, when we're talking about like the amount of work that a system either does or has done on it, we express it in terms of like how much did we have to fight against atmospheric pressure to expand, or how much did we like succumb to atmospheric pressure to compress if we're a gaseous system. Tara?
How do you find the negative P external?
It's atmospheric, right? If we're fighting against atmospheric pressure, then it's whatever today's lab pressure is. Ideally around 1.0 atmosphere, but maybe a little bit different. But it's okay to approximate it as 1 atmosphere. Okay, are we good to move on? Rami, question?
C's a constant, right?
What's a constant?
MC change to T.
Yes. That is the, what is C in Q equals MC delta T? It's a constant.
Yeah. I spaced it.
Mm. Do different substances absorb heat the same? So Michael, you're saying no? I agree with you. Why?
Because like, for example, metal compared to wood, like metal is conductive.
Exactly, right? So Michael's noticing that metals, the things that you use probably in your kitchen all the time to make food, we select metal for those materials to make our food with because metals are very thermally conductive. They can absorb heat very quickly and then also cool down very quickly.
Yeah, metals are indeed very conductive, and not just other things as well. I mean, they're also conductive with electricity as well.
Yep, they are highly thermally and electrically conductive. That is true. So C is a measure of that capacity to absorb and hold heat. It's called your specific heat capacity. And it's unique to every substance. Now going back, Iad, you brought up something that we thought about in Chem 1 that's not shown on this board here. Do you remember? Before that, when I asked you, like, what do we care about in thermodynamics, you said heat, and then there was one other thing we talked about in Gen Chem 1. Had a special variable.
What would work? No.
Work, heat, enthalpy.
Oh, yeah.
Yeah, enthalpy. So let's talk about enthalpy. H. So the enthalpy of a system is the total internal energy of that system plus the amount of work, energy, joules, needed to make the system in the first place. So for example, let's think about you guys actually making a chemical system, like perhaps making a solution. If you wanted to talk about the enthalpy of that solution, you would be talking about like the total internal energy of the solution or solute particles, then plus the amount of energy or work that it took you to physically bring that solution into existence. You had to move, right? You had to displace something. That solution takes up a total volume. It exists under a certain pressure. And the way that we express enthalpy, specifically the change in enthalpy, delta H, is equal to the change in internal energy plus the change in the product of pressure and volume. This is like the standard physics definition of what enthalpy is. This equation looks gross, right? Too many deltas, too many variables. Like, this is starting to get very alphabet soupy. So let's remind ourselves about the purpose of introducing some thermodynamic assumptions that we're going to make as chemists. Specifically, assumption 4. So what was that fourth assumption that we are going to make? Brianna?
The one we just.
Yeah.
Okay. Conditions of thermodynamic system exist at a constant.
Constant pressure. So how would this work? I would have that my change in enthalpy is equal to total internal energy, which we said was heat summed with work, plus now the work needed to bring this system into existence. Of those terms, P and V, that could change. If we make assumption number 4, what's the only one that's going to change? Ivan, what do you think?
What's it gonna change?
Yeah, if we're at constant pressure, then which of these two terms is going to change? Pressure, volume, both?
The pressure.
The pressure is going to change if it's constant?
If it's constant pressure, it's volume.
The volume, exactly. So I'm going to rewrite this as my constant pressure times some change in volume. Well, didn't we just say that work is the negative external pressure times the change in volume of the system? We noticing something here? No? What is this constant pressure that we assume to be at? Claire? What is this constant pressure of our system? What do we assume it was?
Is it at the standard?
Which is 1 bar, or approximately atmospheric. So if I've got negative external pressure, Tara, what is that equal to? Right, atmospheric pressure. Then these two terms are the same term with opposite signs. The pressure that my system exists at is atmospheric pressure. That's what I'm saying. The constant pressure we're assuming is the pressure of the room, or the pressure of the environment in which our chemical reaction happens. So then what happens? We can say then that delta H is equal to Q. So enthalpy, if we're at constant pressure, is equal to Q. This is why in Gen Chem 1, when we were doing things like delta H calculations, we called it the heat of reaction, or the heat of neutralization. Because at constant pressure, enthalpy and heat, Q, are the same entity. So thinking back to Gen Chem 1, we talked about enthalpy, assuming constant pressure, as a means of saying whether we were exo or endothermic. So if we are exothermic, this means that heat has to have been released from the system, meaning that Q product state has to be larger than the reactant state in order for us to be releasing heat out into the surroundings. We had to generate heat as a result of our reaction happening. And what about if we were an endothermic reaction? What, Ivan? Product greater than reactant if heat is being absorbed by the system. Oh, you're right. I have a sign error here. So, Ivan, loudly explain yourself.
So since when you add the reactants, right, reaction creates reaction, the product will end up heated.
Right. Our heat of the product has to be higher because the system absorbs heat. So there we go. Sign error. Yay, dyslexia. Q prod. Q react. So we have to be absorbing. If you need to justify this to yourself, you can look at a little energy diagram. So exothermic, if I were to look at delta H over our reaction time, if this is reactant and product, if I'm going to be net releasing energy, then this must be true. We've all seen these before, right? We've never seen these diagrams? Okay, some of us have, some of us haven't. We'll talk about them later then. Okay, so that was probably like 2 weeks of Gen Chem 1 material in 3 slides. Thermochemistry. So this is like the total knowledge that I'm presuming you have about how we talk about energy in chemistry. You think in terms of enthalpy, aka you think in terms of heat. However, let's talk about this idea of spontaneity. Where have we heard this word before? Like outside of a science class? Tara? Yeah, if you're going to be spontaneous, you're just going to do something just because. No one forced you into it, you're just doing it. It's like my mom's number one gripe about my dad. Why aren't you more spontaneous? Why can't we just go to San Francisco for the weekend? My dad's like, because the city sucks. And I don't disagree. So spontaneous, meaning no outside prompting. I don't have to like make the system do the thing. It'll just do it. So a spontaneous process is a process that occurs without W/O, without external interference, happens on its own, happens on a whim, as Tara said. So for example, if I were to think about a diamond, which is elemental carbon arranged in repeating tetrahedral molecular units, that will spontaneously, without having to like add any heat, apply any kind of work by like making really high pressure systems, eventually become solid and elemental carbon, but in a different structure, one that we call graphite. So this is spontaneous. It occurs naturally. without any external or outside reason to do so. Okay, so I'm saying that spontaneously diamond will turn into graphite. That's true. I'm not lying to you. Yes, Ivy? Yeah, what about spontaneous combustion? I would argue that combustion is not necessarily spontaneous. It just means like that's a colloquial or like local language term for it happened out of nowhere and we don't really know why. But like actually chemically, thermodynamically, that's not spontaneous. Yeah. That was more a problem when people were like falling asleep with cigarettes in their hand because it was 1965 and that's what everyone did, I guess. Yeah. Plastic sheets, cigarette in the hand, not a good combo. All right, if this is true, which it is, then why is it that you can inherit like family heirloom diamonds? Why is it that you can inherit family heirloom diamonds? Sorry, thank you, Ivan. Like, does anyone have any heirloom jewelry?
My mom does.
Yeah, my mom too has some heirloom diamonds from her mom and her grandma.
I don't have any myself, anything like right now, but in the future.
And you know that you're going to, Gabs, like, possess those diamonds at some point in the future, right? That's what it means to be an heirloom.
Well, it's not exactly like diamonds, but yeah.
Sure.
Yes, but and speaking of which, it's funny that you brought up a diamond because this month is my birthday and next week is my actual birthday.
Oh, nice. And April is the gemstone diamond, right?
Exactly.
For the birth month? Okay, happy almost birthday.
April 15th.
15th, okay. So why is it then that Gabs can expect to maybe one day possess an heirloom diamond and it won't have all turned into graphite?
Probably because it just takes a long time for it because, well, the more, from what I can see, the more solid it is, the longer the spontaneous reaction rate occurs.
Ooh, careful.
That's
You're close. You're in the right way of thinking. When we think about like a person being spontaneous, like acting on a whim, as Tara said, it's like an all of the sudden, very quickly, rapid decision that we make to do something. But thermodynamically, spontaneity as a concept is not associated whatsoever with time. So spontaneous does not equate to being fast. A diamond is relatively forever because human beings live like, I don't know, let's call it max 100 years-ish. And this takes like millions of years to happen. It will happen. There's no like energetic prompting that this reaction needs to happen in the first place. It just happens very, 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 very slowly. So we all clear on how this idea of like happening without prompting does not mean it's going to happen fast? Tara? It degrades very, very slowly over time, but yeah, it will just eventually be graphite. Like if you were to take a diamond and then put it in a time capsule and then travel forward in time, like tens of hundreds of millions of years, and then open that time capsule, you will find graphite.
Graphite's process to become that is a lot quicker.
They're reversing this process and using a lot of energy. Like they are then imposing an external energy to make that process happen to fight the spontaneous nature of this direction of reaction.
So how would graphite turn into diamond?
How would what?
Graphite turn into diamond.
How would graphite become diamond?
Yeah.
Okay, so how do we take elemental carbon, which is everywhere, and turn it into diamond?
Pressure.
Yeah, right? High heat, high pressure. Just like how the earth makes it. Ivy?
Does that mean it would hypothetically happen a little bit faster in space or at like a lower gravity?
I don't know how the rate would be affected because I don't know the kinetic model of this reaction. This, I believe, it's what we call a zero order reaction. It's what we were supposed to talk about today in iodine clock, but we're not going to. meaning like the rate will happen regardless of how much of something we have. So that to me I think like pressure wouldn't have an effect, but I'm not sure. We should look that up. All right, why are we talking about spontaneous processes? In order to understand whether a reaction will spontaneously occur or not, we need a full thermodynamic understanding of energy. So does anyone have any other examples of like spontaneous reactions, things that'll just happen? It doesn't have to be even just like a chemical reaction. It could be like something that just happens naturally. Brianna?
It's like metal rusting.
Okay, yeah. Eventually, over time, you leave a car out, it's going to rust. Isn't that what? Yeah, that we can affect the rate of, but it doesn't matter like if we're in the Midwest where there's no, salty atmosphere, or on the California coast where we have lots of salt. That reaction itself is still going to be something that happens without us putting any energy into it.
What if you put it into an environment that has no,
The reaction will still happen.
okay.
What else? Tara?
Are these like reversible?
We are presuming, what are we assuming about these thermodynamically? Right, so like we could maybe have some kind of equilibrium reversibility, but thermodynamically we're saying it's impossible to exactly perfectly recreate the original thermodynamic state of our system. We're being realists here, not idealists.
What about organic matter?
What about organic matter? Yeah, what happens when you leave your lettuce in the fridge too long? What happens?
It starts to degrade.
Yeah, it decomposes. Gets gross.
Yes, and while you could argue that the cool temperature that is inside the fridge does act upon it, that it always slows down. It always slows down the reaction.
Right, exactly. Controlling the thermal energy exchange is a means of controlling the rate of reaction.
Yes, it just slows it down. It doesn't stop it.
Right, even if you were to freeze the lettuce that we're talking about, that would still eventually naturally rot, just like all of you little munchkins in this room. Aging will happen to you personally.
Yeah, it's not something we can stop. I mean, we're getting older.
I resent
every
that
day.
statement.
I'm just saying, you have to come to terms with it.
I have lines under my eyes.
You are still metabolically aging. You should all wear sunscreen, though. Okay, so people spontaneously age. Organic matter spontaneously decomposes. Diamonds spontaneously become graphite. Cars spontaneously become rust. These are things that just happen. What, Ivan?
Joy becomes sad.
Enjoy being upset?
No, joy becomes sad.
I don't know what you mean.
Like spontaneous process.
Okay, sure. Okay. Let's take a break. And then we'll come back to answer this question like, well, why are things spontaneous though? Why does aging have to happen to me personally? Right? Let's answer that question in a minute. So let's take a 5-minute break and then we'll come back.